Okay, so welcome back to the lecture series of finite volume, and what we are discussing is now, after finishing the incompressible fluid flow problem, we are now in the middle of the compressible fluid flow problem. And once we do that, then we will discuss some of the special topics, and there, essentially we will just touch upon those special topics, how to discretize and implement in the finite volume context. So, let us go back where we left in the last lecture is in the compressible pressure based corrections, and where once you try to look at the pressure correction equation, this is where we started with the pressure density relationship, then we use the Taylor series expansion to get the density, where one component is the star component. Again, this case, like our incompressible case, you have a correction component which is prime and the intermediate component which will be calculated like a star. Then the density prime was obtained like this, and once you put it back in the discretized continuity equation, this is your discretized continuity equation, you get this equation, and where m dot f is m dot like this, and this term here which is can be treated as intermediate m dot f star, and this is m dot f prime. The second order correction term like rho a prime v a prime dot s f prime s f. So, which is this term, the second order correction terms, these are neglected. So, then because this term is typically smaller, so once you neglect that, the approximation does not influence too much the iterative process or the solution process, which is now we use the Riochow interpolation. So, similarly Riochow interpolation is applied, and at the flux, a mass flux at the cell face can be obtained like rho star f v star f bar dot s bar, and then so this is equivalent to your rho f star v f star dot s f, and here m f prime is rho f star v f prime bar dot s f minus rho f star d f b minus pressure corrections equation, and then one contribution come from the C p, and if you do the algebra, finally you get this expression. And again the second order term which is shown here, the underlined term, these are actually neglected in the iterative process. So, now the second order term here it is neglected, and the underlined term which is here, that actually presents some difficulties as was done in the incompressible algorithm. So, typically this one also sort of dropped or neglected, and if you neglect this term, the correction to the mass flux or m dot f prime becomes rho f star dot s f and this much. So, now your corrected mass flux is looks like that. The first term here is similar to what arising at the incompressible case. So, if you look at the first term, this is exactly the kind of term that you have seen in the incompressible case, and second term is due to, so this is due to density correction. So, this is due to density correction. Since it is a compressible case, the density corrections do appear in the system. Now, in the compressible system, the second term is quite important because it transforms the pressure corrections equation to an elliptical system, and 2n1 also in a other format. Now, at the same time we can devise our simple algorithm or compressible simple algorithm based on this. Now, one can do some sort of a normalizations of this term like m dot f star dot s f into C p f by rho f star. If this kind of normalization is done of weighting factor 1 for p f prime term, which will be proportional to, now becomes an weighting factor p f prime terms which will proportional to 1 by Mach number square, where m is the Mach number. Now, in that case the m dot f prime would be RT rho f star by this and like this expression. So, when you have a low Mach number values, the delta p correction term dominates and that returning equation is actually elliptical in nature. But on the other end, when your Mach number is too high, so the p prime correction and can no longer be neglected, which will given rise to a hyperbolic character to the correction equation. So, this combined behavior actually allows the prediction of the fluid flow of all the speed. That means, there is a strong correlation between Mach number and pressure. So, and that changes the system behavior accordingly. When Mach number is low or the low Mach number cases, rather incompressible cases, your delta p prime equation behave like an elliptical system, but when you go down to high Mach number cases, they behave like an hyperbolic system. So, now once you substitute everything back in the continuity and compressible form of the pressure corrections equation, so this will be the transient term Vc by delta t Cp Pc prime summation over cell faces and then you density correction. So, you can put them together nicely in a compact form, and same thing once you put the and at the treatment of the underlying term yields the variant of simple. So, how you actually treat this term, this gives you various simple algorithm, which we have already seen in the case of incompressible flow, where simple, simple C, prime or piezo, it depends how we take care of this correction term. Now, dropping the underlying term, the pressure correction equation for the simple algorithm can be modified like Vc C rho by delta p, and so this is a transient term, this is convection like term summation over all the phases due to density, diffusion like term, and then which will be a right hand side you have a source and corrections. So, that is a source term. So, this is your p prime equation for compressible case. Now, one can note that because at convergence the correction fields always leads to 0. So, the order of scheme used to discretize this convection like term is of no consequence on the accuracy of the final results. So, however, there is not the case for m dot f star. The use of higher order schemes in its evaluation can improve the capture of shocks in the algorithm. So, to enhance the robustness, and it is helpful to use the upwind scheme for the discretization of this convection like term. One can actually neglect the non-orthogonal contribution for the diffusion like term, and then the pressure correction coefficients would become like this. So, AC PC prime summation over all these would give rise to this source equation. That is my discretized equation for P prime in compressible case. AF P prime would be minus rho f df minus mass flow rate m dot f Cf rho f. AC P prime would be Vc C rho by delta t summation over all interior faces Cp m dot f and then correction, and rho this will be behaving like an, so you have one along the face, another on the tangential. So, this is like an non-orthogonal corrections, and this can be neglected, but this will only once you neglect that your convergence would be slower, but eventually since it is a iterative process you will end up getting a converged solution. Now, once you do that, your corrections components can be estimated. Once you get the P prime from this, once you get P prime, then your Vc star star equals to Vc star plus Vc prime, where Vc prime equals to minus dCV delta P prime C, and Pc star is Pcn and lambda. So, here you use some sort of a under relaxation and the factor is lambda, because lambda p, then rho c star star equals to rho c star plus lambda p, I mean this also for some sort of a under relaxation for lambda rho, and then finally calculate m dot f double star equals to m dot f star plus m dot prime, and m dot prime is estimated like this. So, you have different under relaxation term and you get the corrections term. Now, top of it one has to also discretize the energy equation. Now, before doing that, I mean to get the discretized energy equation, we can look at the different terms which are part of the energy equation. For example, first thing that we can look at the specific heat term. So, the other terms in energy equation. So, the specific heat term, that if you look at the volume integral of that, it will get a corrections and the previous iteration value, and you can write that term like this, where if you see there is a d Cp by dt sitting there, which is a material derivative or substantial derivative of the specific heat. Now, as long as your flow is incompressible, you can actually neglect these terms, or the contribution due to this become essentially 0 in incompressible cases. But since we are discussing the compressible case, we cannot neglect this term, and this leads to the some sort of an transient and spatial derivative of that. Similarly, the pressure term or the substantial derivative term, which for the pressure, if you do that, this will be dP by dt star at C Vc. Again this will retain some transient plus spatial component. So, you need to take that also into account. Now, you have, this is your viscous dissipation term. So, the viscous dissipation term, if you do the volume integral, this will only get you back a volume integral with the corrections. And the other term is the, if you have any source or sink like term, then you get a volume integral of that, which will return like that. Now, this would be source or sink term. So, this guy is the dissipation term and this is your viscous dissipation term. So, correct that thing. So, first term is the only dissipation term, this is the viscous dissipation term where mu is sitting there, and this will be the source term which will be integrated. This we have already seen. The only thing which is the new term arising, even then if you have a viscous dissipation term, all the it only actually gives rise to the velocity gradient. Apart from that, the integration over a cell element is not that difficult, but the difficulties arises from this dP by dt term and dCp by dt term. Now, if you took the energy equation, and this will be your discretized form of the energy equations, discretized form. Again it looks like similar to our momentum or anything else. So, AC Tc summation over cell AF TF, but the superscript T stands for the temperature. Coefficients AF here minus KF, EF by DCF minus mass flow rate CPF. ACT is AC dot minus here again dot, this guy is the transient contribution. So, this is a transient contribution minus this, and the transient contribution is rho c, CPC, Vc by delta T and AC naught, and the subscript from T minus delta T, and without superscript is at T level, which can be calculated like dCp by dt, and the source term you have sum over the phases, then Cp temperature deferred correction. This is the deferred corrections where you take the high resolution and the upwind corrections, previous time integration and this. So, now if you look at the coefficients here, they are bit involved, and why they are bit involved? The reason is because of the compressibility. Since it is a compressible flow, the pressure density and the other quantities like Cp, they are connected and one cannot neglect from one other. Top of that, you come across like this kind of special the material derivative or substantial derivative term in your discretized equation. Now, having said that, we can actually, this is our simple algorithm for compressible case. So, we can see, so initially you do the guess value as we have done, you solve for the momentum for V star, then do the rho star calculation and then m dot f star, where you use rho chow interpolation, solve for p prime, then you correct, then again you solve for temperature, then you update everything. It is just like a simple algorithm, only thing is that density is now taken into consideration and you take that into consideration. If it is converged, move for the next time iteration, if not, you go back and this place and repeat. So, the algorithm wise it is exactly similar that we have discussed in the incompressible case. The difference comes here, density, Cp, these are the terms which are no more can be neglected, and top of that energy equation becomes a part of your solver or the system, you cannot avoid the energy equation. Now, having said that, one can understand when you talk about this algorithm, you need to talk about the boundary conditions. We have done some detailed discussion for the incompressible case, now we will look at the same in the context of compressibility. So, this is a typical boundary element and here is the SB is the surface vector, this is the C centroid, and now in the boundary cell this is my continuity equation, rho C star. So, this is my continuity, rho C star plus rho C prime minus rho C from the previous time iteration, mass flux correction and boundary phase. So, the boundary phase velocity would be corrected like an Ryu-Chow interpolation using the pressure and this, and the corrected mass flow rate or the calculated mass flow rate would be rho v with the previous iteration, and this is the corrections. So, when actually now if you have a different kind of boundary condition, this term of the system of equation they get modified and they look quite a bit of similarity except the term where your density these are coming in for the mass flux calculation. Other than that, they are they are looking quite similar. Now, the first thing is that inlet boundary condition. Now, inlet boundary condition, if you have a subsonic flow, that means now while you talking about the compressible case or high speed case, you can encounter two different kind of boundary condition. One could be subsonic, one could be supersonic. So, let us first start with the inlet but subsonic flow. If it is subsonic flow, and then it could be specified velocity. If that is the case, your Pb is not known, m dot b is not known, but Vb is specified. Now, like incompressible flow, for compressible flow the density depends on the pressure. So, the mass flux remain unknown even with the specified velocity. See, that is the big difference. When you talked about the incompressible case, as soon as you know the velocity you could calculate this, but in this case without knowing the density you cannot do that. So, that means m dot b prime is equals to rho b prime Vb star dot Sb, which is not 0. So, at the inlet boundary the coefficient is multiplied with the Pb prime and it could be written as AB Pb prime Cpb by like this. Now, for the implementation of the pressure correction, Pb prime is expressed in term of some interlinear node and the coefficients like this. So, ACP prime would be BC C rho by delta T by CPF by rho F star m dot. So, these are coming from the interior phases, this is some boundary phase contribution. So, this gets modified for the pressure. Now, the another could be you can specify static pressure. Static pressure, that means PB is known and also this is known velocity direction, what we do not know this and this we do not know. Now, in this case for static pressure known, the PB is known. So, PB prime can be set to 0 and consequently your rho B prime is also 0. Now, the implementation would be similar to incompressible case like a Dirichlet condition, and the correction term coefficients for pressure gets modified like this. So, one would be the transient component, then you get summation over all the phases CPF rho F star m dot F plus rho F dF and rho B dC. So, this is a boundary phase contribution, this is coming from all interior phases. Now, another kind of boundary condition that we did not talk about in the context of incompressible flow, which is quite important here when you define the specified P naught or the total pressure and velocity direction. So, that means P naught B is known, EV is known, so which means m dot B is not known, VB is not known. For this case, to calculate the magnitude of the velocity, one has to use the stagnation conditions where Mach number at the phase can be defined at Vb dot Vb by gamma Tb, and the pressure which is unknown at the phase can be correlated with this standard isentropic law, which is stagnator condition is known. So, the pressure can be correlated with gamma. Now, here B refers to the boundary. Now, Pb one can rearrange with gamma by m dot F by rho B like this. So, which you can get rid of Mach number and velocity. So, it can be terms of total pressure, one can actually rearrange this. Since EV is a unit vector in the direction of the velocity, so once you differentiate this equation, so differentiate this equation with respect to m dot star B, which will get you dPb by this. So, that is an algebra, one can carry out that, and now you substitute this guy into the equation of the pressure corrections, then what you get, Pb prime equals to Cb some constant like this. So, that will get you back the mass flux prime like this. So, these are the condition which you get for the pressure correction. Now, the modified shell coefficient which is obtained for the m dot B from this equation, you can apply that and the pressure corrections equation get modified like this, where this will be transient term rho Cp by delta T, then you have a term which is interior phase term and you get a term on boundary, and your stagnation temperature would be estimated like this. So, in a compressible case, your pressure density temperature they are linked, and whenever you do in conditions with the pressure, then you can have, you need to take care the density and temperature at the same time. Now, that talks about different kind of boundary conditions at subsonic case. Now, you could also have inlet boundary condition which is supersonic in condition, that means Mach number is greater than 1. So, in that case you can have again a situation where specified static pressure, that means Pb is known, Vb is also known and Tb is also known. So, it is specified P, T and V. So, all three are defined, then which is a implied condition like m dot P prime Pb prime, they will be 0, and the coefficient of the pressure corrections equation gets modified like that. So, it will retain the transient term, and this is the term which is the transient term, and there will be a integration over all the interior phases. So, there will be two contribution which will come from this. So, one can note here your inlet conditions in compressible cases could be of two different types. One could be subsonic, one could be supersonic. So, now when you have a supersonic, you do not have too much of variation, you can specify them as a Dirichlet condition. Now, similarly, you should have outlet boundary conditions, and outlet boundary condition could be also subsonic flow, where again you can have specified pressure, which means Pb is specified, m dot b is not known, Vb is not known. So, once specified pressure, your Pb corrections would be 0, and the mass flow corrections can be estimated like this, where rho b star dc Pc prime is computed, and since the Vb star is not known, it is necessary to assume that Vb star is equals to Vc star, and the expression for the pressure correction coefficient Ac would be modified like Vc Cp by delta T, and then you have all this contribution from the interior node. And also one has to note that energy equation, a 0 gradient or del T by del N kind of 0 at the energy flux 0 or Neumann kind of boundary condition needs to be specified, because this is a supersonic case, you cannot leave the energy equation unconnected. So, it has to be connected with the system. Now, similarly, one can have specified m dot. So, that means m dot A B is known, but Pb not known, Vb not known. So, specified mass flux means m dot prime would be 0. So, you can simply drop the pressure correction equation with no modification, and then if setting m dot b prime equals to 0, the coefficient of the pressure correction equation or Pb prime would be like this. So, you can actually calculate the pressure and density corrections at the boundary. And the last one which I would like to just touch is the outlet boundary conditions, and which could be of the supersonic type. So, in that case, here the none of the variables should be specified. So, P, V and all these are not known, P, V, density, temperature, and they should be extrapolated from the interior value. So, m dot b and Pb, they are interpolated or extrapolated from interior cells, and this is equivalent to applying a Neumann kind of boundary conditions on pressure corrections. So, which will lead to this, so which is equivalent to Neumann kind of boundary condition for P prime equation, which will lead to this pressure correction coefficient to be modified like that. So, Ac prime would be Vc 0 delta T, this is transient term, and these are all summation over interior phases. And if you notice here again, pressure, density, temperature, P, rho, T, these are all connected. So, when you compare with the subsonic case with the supersonic case, the one important difference which appear is that the not only the formulation, because formulation only takes care of the takes the energy and density into system, also there this pressure, density, temperature, they are connected, that is number one. Then you have to involve the energy equation, that is another involvement or inclusion, and also in the discretization you get some sort of a term like dP by dt, dCp by dt, these are the term which appears, and then viscous dissipation term, These are the term or extra term which appear in this kind of situation. Now, the other thing which is possible is that when you come to compressible case, your solution algorithm has to have two different kind of definition of the boundary, inlet condition and outlet condition, they could be of. So, all your boundary condition can be of inlet or outlet, could be of subsonic type and supersonic type. So, one has to take care of that. Now, that essentially concludes the portion of our fluid flow problem, where we have discussed both incompressible and compressible. Now, what I would like to touch upon some of the advanced things like how you generate grid, but this would not be done in a detailed discussion, but one can always look at the textbook and then look at some of these turbulence modeling issues and how you discretize that. So, we will stop here today and we will take from here in the follow up lectures. Thank you.